Okay, so we're into chapter 4 here last time, and we're talking about really the atom. And I think we talked about some important experiments that sort of led to our understanding of the atom. Um, again, basically, atom is mostly empty space. Has that positive core, which is our nucleus. And as we talked about, that's where we find our protons and our neutrons found. The electrons are out about from the nucleus, again traveling in a random sort of pattern, but again there is an attraction between obviously the negatively charged electrons and the positively charged nucleus that sort of holds them there so they don't just fly away, if you will. And really that the major or most of the mass of the atom is the nucleus. And again, that is obviously where we find our protons and our neutrons. And as we saw, each of them are individually about 1,800 or so times heavier than any electron that's flying around. So that makes sense that most of the mass of the atom is made up of the nucleus. Remember as well that it's actually the neutron that is slightly heavier than the proton. So it is the heaviest of all three of those subatomic particles. We also talked about towards the end a couple important sort of aspects of atoms like isotopes. And isotopes, again, are the same element, but they have different masses because they have different numbers of neutrons. And this is one of the reasons of Dalton's atomic theory, like we talked about, that's incorrect because of the existence of isotopes. Remember, he said that all atoms of the same element will be identical to each other. So obviously these are the same element. Their atoms will not be identical because they have different numbers of neutrons in this case. We do write the symbols for the atoms or the elements. And typically to the top there, we do our mass number. Bottom left there, we do our atomic number. And remember that our atomic number is the number of protons there are. Our mass number is the number of protons plus the number of neutrons. So if we subtract again the mass number from the atomic number, that will get you your number of neutrons. The important thing is a couple of those things that we talked about, which is all of those things, the mass number, atomic number, protons, electrons, and neutrons, they all should be positive whole numbers. And that is why when we go to the periodic table, the only number that we could find is the guy that's up on top, which is our atomic number. A reminder that the number on the bottom is not the mass number, but that's actually the atomic mass. So this is not the mass number. And again, as we talked about, the easiest way to remember that is pretty much none of those numbers are whole numbers on the periodic table. So you know it has to be a whole number. So that again is a good way to remember that. Any questions on any of that stuff there we talked about last time, I think? All right, so before we sort of move on, I think we did protons, electrons, and neutrons. But if we did have something that said that did have a charge, and things that have a charge are what are referred to as ions. And again, there are really two types of ions. There are cations, which are positively charged, and there are anions, which are negatively charged. So if we did have something that did have a charge, so for example, if we had, say we had chlorine 35, 17, and -1 in this particular case. So if we had this versus, say, the neutral version here of this, in our neutral version, we would have 17 protons in this case. We would also have 17 electrons to balance it out to a 0 charge. And in this case, we would have 35 minus 17. And again, that would get us our number of neutrons, which is taking our mass number minus our atomic number, which is 18 in this case, which is the number of neutrons. Now, when we go to our guy that has a negative charge here, and this is an anion because it has a negative charge. This guy will have, in terms of numbers of protons, will be 17. In terms of its number of neutrons in this example here, it will be the same. But now when we talk about electrons here, it will have 18 electrons in this case. And that's because 17 positives and 18 negatives will leave you a -1 left over. And that is where the charge comes from here. So things that have a negative charge actually gain electrons. And we can see that if we compare the neutral guy has 17 electrons. Guy with a -1 charge has 18 electrons. And that is what a negative charge means. It means that it has gained electrons. The actual number of the charge is how many electrons it gained from the neutral atom. So what we know about the neutral chlorine is it has an atomic number of 17, which means it would have normally 17 electrons when it's neutral. So basically, if you just take the atomic number and add one more electron to it, or one more to that, it'll give you the proper number of electrons. Question on that there. So this is again a result of gaining electrons. Now, if we look at, say, something like, I think we had this guy the other day, iron 56, and we had iron, say, with a +3 charge. So here in our neutral, the atomic number is 26, which means it should have 26 protons. Once again, because it is neutral, it will have an equal number of negative charges, which gives us 0. And once again, that's why there's nothing written there. It has no charge. And our number of neutrons in this case would be our atomic number. I'm sorry, mass number minus our atomic number, which was 30 in this case. Now, when we have the same sort of guy, but it has a +3 charge, once again here, the number of protons will be our atomic number, which would be 26. Our number of neutrons will be the same as here, 30. And our number of electrons in this case will actually be 23 electrons. 26 positive charges, 23 negative charges, leaves you 3 positive charge left over. And that is, again, where the charge comes from. How come it is the electrons that determine the charge and not the protons? What happens if I change the protons? I change the element, right? So we can now change the protons. Otherwise, it's no longer the same element. And obviously, neutrons have no charge, so that's not going to do anything to affect the charge. So the only thing that affects the charge is the number of electrons in this case. And as we compare the neutral iron in this case to the iron with a +3 charge, what we see is the neutral iron has 26 electrons. The one with a +3 charge has 23 electrons. It actually has less electrons than it started with. So it actually is made by losing electrons. And that's what a cation does. It basically will lose electrons. And how many electrons it lost from the neutral is the actual number that you see on the charge there. So a +3 charge means that it lost 3 electrons. So once again, if you know or see the positive charge, you know it lost electrons, and the number is how many. So if you know the atomic number again for iron, which would be 26, and you know in a neutral situation it should also have 26 electrons, all you have to do in that case is subtract 3 from that number, and that'll give you the proper number of electrons. Questions on what happens with charges? Why don't you try a couple? Let's do Mn. We'll do 25, 54, and we'll do a 4+. And let's do phosphorus here. 15, 30, 3 minus. All right, how many protons, electrons, and neutrons in each? Okay, let's take a look at the first one here. So we'll take a look at this guy here. So obviously, we could still use our number of protons, which is our atomic number, which is the bottom number there, which is 25. In this particular case, it has a +4 charge. So when I see the plus, I know it has lost electrons, and it's basically lost 4 electrons. So really, you could just subtract 4 from the atomic number there, and that'll give you the proper number of electrons, which in this case should be 21, I believe. And that will give you basically that +4 that's left over for the charge there. And in terms of our neutrons here, we'll take our mass number of 54 minus 25, and that's going to give us 29, I believe. There. Any questions on any of that one there? The bottom one here, once again, we'll start with our protons, which is our atomic number, which is 15 that we could get from the periodic table. In this case, we do see a negative charge. And again, negative means that it's gained electrons, and the number is how many it gained. So that's 3. So once again, the quick way, you could just add 3 to our atomic number and our number of protons, which would mean I need 18 in this case. And that's going to give me 18 negatives and 15 positives, gives me that -3 left over, which is again where the charge comes from. And lastly, our number of neutrons in this case, 30 minus 15. Should be 15. Questions on either of those there? So obviously, you do need to be able to figure out protons, electrons, neutrons, neutral things, things with charges, mass numbers, atomic numbers. Any questions on any of that? Okay, so isotopes, as we talked about, are really the sort of same element. And because really most chemical reactions, pretty much all chemical reactions involve only the electrons, one of the nice things about it is the neutrons really don't play a part. And because of that, nothing in the nucleus plays a part in normal chemical reactions, which means a lot of isotopes are radioactive isotopes. So in a practical aspect, a lot of times people will use a radioactive version of a particular element. So for example, if you're doing some type of research where you're interested, say, where copper goes in a sort of reaction or something like that, and you want to kind of follow copper through the entire reaction, you could use a radioactive version of copper, like copper 64, which I've used before, copper 68 as well. And you basically could use it as a label. You could basically follow the radioactivity, and you know pretty much where all the copper goes. The radioactive version, say, of copper and the non-radioactive version of copper basically will do the same chemistry in the body. So you could use it to your advantage to sort of follow what's happening in. And that's a very common procedure people do in research, is they use radioactive versions of elements so they can really sort of follow what's happening along the way. Any questions on that? All right, so to our periodic table here. That's the periodic table. It looks good. Periodic table, obviously, like hanging on the wall, is an arrangement of all the elements. Right here as well, apparently, another periodic table. Let's talk about some of the things on the periodic table. So first off, elements in a column on the periodic table are known as a group, or if you're really old like me, a family. Not too many people call it families anymore. Most people call it groups these days. And when we talk about the groups, there's a lot of different numbering that you see on the periodic table. You'll sometimes see A numbering, you'll sometimes see B numbering, and you'll sometimes just see regular numbering 1 through 18. So most of the time in pretty much all your chemistry classes, we do use the A numbering, which is the representative numbering. And that means that group 1 is here. By the way, group 1 actually starts with lithium, not hydrogen, and we'll talk about it in a second. Group 2 is right next door. We skipped the middle there. That's group 3. Group 4 here, group 5, group 6, group 7, and group 8. So we really do use the A sort of numbering. Most of the time, people don't include the A, so they'll usually say group 1A or group 2A. They just usually say group 1 or group 2 most of the time. So that is groups, again, going up and down there in a column. Also going left to right on the periodic table are periods. There's 7 periods on the periodic table. 1, 2, 3, 4, 5, 6, and 7. And periods are heading in that direction on the periodic table. We already talked about it previously, but again, our number that we see above the symbol there on the periodic table is our atomic number. And again, that is our number of protons there are. So as we talked about last time, again, the definition of atomic number, which is often missed by people, is just the number of protons. So remember, a neutral guy will tell you the electrons, but the actual definition is just the number of protons that are present. And as we talked about as well, that's a really important number, as every element has its own unique atomic number, which means if you know the atomic number or the number of protons and you have a periodic table, you should pretty much know what element you're talking about by simply just looking it up there on the periodic table. Now, the periodic table is broken up into really 3 sections, and on most periodic tables, you can kind of see the staircases sometimes referred to right about here, starting at boron and kind of working its way down. And kind of to the left of the staircase, these are metals. Also, the 2 rows, which are not pictured on this periodic table on the bottom, are also metals there on the bottom. Upper right of the staircase are nonmetals. And what the staircase are what are referred to as metalloids, are semi-metals. And metals are good conductors of heat and electricity. They can be hammered into sheets. They can be pulled into wires. They have a really shiny appearance. Most metals are solid at room temperature, except for mercury, which is why mercury there is blue on that periodic table. So a lot of times you'll see mercury kind of a different color than everything, all the other metals, but most of them are going to be solid at room temperature. Now, nonmetals, which again are to the upper right there of the periodic table, pretty much have opposite characteristics of metals. They are bad conductors of heat and electricity. They're dull, they're brittle, they're used as insulators. And very often they do have a much varied sort of state. So some nonmetals are gases, some are liquids, some are solid. And a lot of our nonmetals are those diatomic molecules that we talked about, H2, N2, O2, Cl2, F2, Br2, I2. So remember that these are our diatomic molecules, which are also elements. And that brings us back to this guy right here. That's hydrogen, that's lithium. Hydrogen is what type of metal? What type of compound? Hydrogen is a non-metal, right? So lithium is a metal. So hydrogen, although it's hanging out here on most periodic tables over there with all the metals, hydrogen is actually a non-metal. If you're old like me and they used to print periodic tables, you oftentimes would see hydrogen sometimes on both sides. They would oftentimes put it, they don't do that too much anymore, but hydrogen is actually a non-metal. And that is why group 1 there actually does start with lithium, which is a metal, and hydrogen is really not part of it. It's over there because honestly, it has a lot of properties and sort of acts a little bit like a group 1 sort of metal, and has a lot of very similar characteristics in terms of how it sort of interacts. But it is actually a non-metal. It is one of those diatomic molecules like H2. Now, the metalloids, which are sometimes called semi-metals, is that staircase that kind of runs down there. Some books will include boron, some books will not. But metalloids have basically characteristics that fall pretty much on both sides of where they're located, which means that the same element can be have some properties that are very similar to what you see with metals, and the same element can have some properties that are very similar to what you see with non-metals, so like semiconductors. So they kind of have the same type of properties on both sides. And that kind of makes sense where they're located. They're almost like a transition point between, obviously, the metals to the non-metals as you go up on the periodic table. Now, some groups do have special names that you do need to be aware of. And starting with group 1, which is over here, which once again starts with actually lithium. That is what is known as the alkali metals. Right next door, where we have beryllium, magnesium, calcium, those are the alkaline earth metals. Alkaline pretty much means basic. And group 1 and group 2 on the periodic table is where a lot of strong bases come from, like sodium hydroxide, potassium hydroxide, calcium hydroxide. So if you kind of throw OH, which is hydroxide, with anybody there in group 1, you get really a base, and that's why they kind of have that name alkaline, or alkaline represents usually basic. Group 7, which is right over here. Those are our halogens, and those are our fluorine, chlorine, bromine, iodide. Those are mostly diatomic molecules, how they naturally come. Those are the guys come to us twos. And as we'll see right next door in group number 8 is the noble gases. And noble gases are chemically inert. They're very happy. They're very stable. In fact, as we'll talk about when we get to the bonding chapter, that's pretty much the whole point of all bonding is for everybody to have the same electron configuration as the noble gases because they're very, very stable. So everybody sort of tries to achieve the same electron configuration as those guys. They're in group 8. So a little bit more about some of the halogens there. They are very reactive nonmetals, and they do react with metals to form ionic compounds. They also react with hydrogen or H plus to form acids. So if you have something like HCl, that's hydrochloric acid. HF is hydrofluoric acid. So they do make acids when they react with them. As we talked about, they come as diatomic molecules. Most of them are gases. Some of them is sort of like a vapor over a liquid. And iodine there is our purple sort of color solid. As I mentioned before, noble gases used to be called sometimes rare gases. Occasionally that pops in, but it's basically noble gases. Again, they're chemically inert, which means they do not react with others, but they will react with themselves, but they really won't react with anybody else. The 2 rows on the bottom of the periodic table are set aside not to make the periodic table too wide. And that's because if you look at the atomic number, you got like 57 and 72. The missing number is right about there. So that row right there actually goes right about there on the periodic table. And if you follow the number here, 89, 104, the missing number is 90. So those 2 rows on the bottom actually go in that spot. They don't do that because then your periodic table is giantly wide. The only place I've ever seen it is actually like 2 doors down. This building, they have one on the wall, and it's like those 2 rows, and the rest of the periodic table takes up the big wall that they have up here in front. These are called the lanthanides and actinides because those are the 2 elements that they should follow on the periodic table. We don't deal too much with those. That's a lot where you have especially the bottom row there. That's a lot of radioactive type of elements, man-made elements, ones with the nice names like California, mycelium, those type of things. So that's where a lot of those guys are. And again, this class, we don't deal too much with it. I would say probably the only element that will probably maybe pop up in terms of knowing name is uranium is, a common one that sort of pops up in questions and stuff like that. But the other ones, maybe not too much. We won't deal too much with this. Now, between group number 2 and group number 3, which is right about here, everything in this region, this is our transition metal region. And transition metals are metals that, for the most part, can form multiple types of charges. And that's really important when we talk about naming, which are coming up next, because they can form multiple types of charges. They have a special way that they are named. That's also why these 2 rows on the bottom, which should go right there in the transition metal region, are sometimes referred to as inner transition metals. So sometimes those guys are referred to as inner transition metals on the bottom 2 rows because that is where they should kind of go. Any questions on that there? So obviously the characteristic shape of the periodic table is put together to have like things near each other. And obviously, as we move from left to right, we are moving more from metal to non-metal. So as we kind of cruise this way on the periodic table, going from metals to non-metals, again, you do need to know where groups are. You do need to know which way periods go. You need to know the names of those groups that we talked about, the alkali metals, alkaline earth metals, halogens, and noble gases. You need to know where the transition metals are. Any questions on any of that there in terms of the periodic table? Yeah. What's that? No, you don't need to know if you're asking like the atomic mass on the bottom, you don't need to know those numbers. And in terms of electronegativity, yeah, it does. Yeah. So as you go to the right, it does increase. So we'll talk about those trends. Maybe here we'll talk about our next one of those chapters will hit the trends, and then you'll need to know those things. Yeah. Other questions? Yeah. So let's talk a little bit about the natural states of atoms. Again, there's also, in addition to noble gases, there are some noble metals, and gold, silver, and platinum are noble metals. They're virtually unreactive. You could hit gold with some nitric acid and it ain't going to do anything. That's how they test sometimes. If it is real gold, they put some nitric acid on it. And if it's still there, then congratulations, you have gold. If your necklace goes away, then not so much gold. Now it'll turn probably greenish and stuff like that when it does it. But they're very, very unreactive. And that's right there. Gold is AU and silver there is AG. AU, AG, and then obviously our platinum there is PT to the left. All right, so as we talked about, our noble gases, again, very unreactive. And we have our noble metals, which are really the same. They are important and they are part of group 8. And as you know anything about bonding, which we'll talk about, 8 is a magic number in bonding. It's really because everybody's trying to be just like the noble gases. As we'll talk about in terms of bonding, they don't become the noble gases, but they're exactly like them in terms of their electrons. So they still are the same elements, but they try to make a very stable electron sort of situation. All right, so we talked about some of our diatomic molecules, obviously, that come as 2s. And we can decompose water, for example, into its elements. And again, this is a compound that can be brought into its elements, right? So these are both elements. In this case, that happens to be molecules. And that brings us back to that definition of molecules that we talked about, which again is really like a basic definition of just 2 or more atoms, which could be the same, or different elements do make molecules. Okay, here's some of those guys we're talking about. Now, when we talk about solid nonmetal elements, they do have a variety of sort of shapes and a little bit different than those in metals. We can have different forms of the same element that's like a nonmetal, and that's sometimes referred to as allotropes. And for example, carbon, there's a few different versions of carbon, and really depending on how carbon's sort of put together in these guys, we get these different sort of properties. So carbon could be diamond, carbon could be graphite, and fullerenes, which are giant, like ideally soccer ball looking 60 or more carbons together. That's what fullerenes are. So this is the arrangement of a carbon in a diamond. And this is more arrangement of carbon in graphite, like, you know, pencil. Clearly costs more when it's arranged on the left there than it does on the right. But you could try to give somebody a pencil and go, hey, it's the same element as a diamond and we're all good, you know. Wear the pencil around your finger. Right? So ions, as we talked about, are things that do have charges. And again, as we saw in those examples when we were doing our atomic number and mass number, there are cations and anions. And cations, which are positively charged ions, once again, is a result of losing electrons. And we could kind of show that in sort of a equation form. So for example, if we took sodium and we started with neutral sodium, when it loses an electron, we could put it on the product side of the reaction, our equation. And electrons would be on the product side like it's being given off or lost. In a reaction or equation, reactants are our starting material. So we're starting with something that has no charge. As it goes through, it's going to lose that electron. And when we see it in an equation, the electron will be on the product side, like again, it's being lost or being given off. And again, this is a cation, which is a positively charged ion, as we saw, results from a loss of electrons from the neutral atom. Now, magnesium, we could also represent the same way. Magnesium will go here to magnesium plus 2 electrons. In this case, magnesium will lose 2 electrons, again, on the product side. This is our reactant, our neutral guy where we're starting. And aluminum will lose 3. By the way, electrons, as we'll talk about when we talk about periodic sort of trends, electrons actually do come off one at a time. They actually don't pop off all at once. So for example, if you had something like magnesium, what would happen is magnesium will lose one electron. Then that guy that has a +1 charge will then lose another electron and become +2. And it actually happens in a stepwise fashion. And as we'll talk about, there's something known as the ionization energy. And the ionization energy is the energy that's required to remove an electron, basically. So as each electron comes off, we have different ionization energy. So for example, this first one here would be the first ionization energy. To remove the second electron, it would be the second ionization energy. Is it easier to remove the first electron or the second one? Which one's easier to remove? It's actually easier to remove the first electron. The first electron comes off as something that's neutral. So once you pop off the electron, what happens to the size of that guy? Does the atom get sort of smaller or larger when you lose an electron? It actually will shrink, right? You lost an electron in its electron cloud. So as it loses an electron, the overall size of the positive ion actually will be smaller than the neutral guy because it's lost some electrons along the way. That is why the second one is much harder, because those electrons are now much closer to the nucleus, which is the positive charge, and that's going to hold them tighter. So it takes more energy to remove the second electron. And if you want to remove a third electron, it would take even more energy, because every time you kind of lose an electron, those electrons that are remain get closer and closer to the nucleus and are going to be held tighter because of that positive charge that occurs. So actually, the first ionization energy is always larger than the second. And in the case, this is also why in certain cases, things will only make a certain type of charge, like magnesium will only make actually a +2 charge. And that's because when you try to rip off the third electron, you're actually into what are referred to as core electrons, ones that started really close to the nucleus to begin with, and now they're even closer because they've already lost 2 electrons. And good luck trying to rip that off. It's not going to happen in terms of energy. It's like almost like a 10-fold jump in energy that you would need between the second electron and like the third electron to try to rip it off. And it's just not energy efficient, so it doesn't really happen in that case. Any questions on that there? Losing an electron will make it, in a sense, it is more reactive in a sense, because when things do become charged, for example, the place where we see really things that have charges in most cases are their ions, and they basically will end up in the solution, float around free to go, and they're ready to react. So in a sense, they are good to go in terms of reactivity, because they're floating around, they're free, they don't have any bonds to break, they're good to go to start reacting. So in that sense, they are quite reactive. And there are degrees of things that will be more reactive depending on where they're located in the periodic table. Other questions? Yeah. What happens to electron gets dropped? It usually will go and find a non-metal, for example. That's usually what will happen when we talk about bonding. An ionic bonds between a metal and a non-metal, and usually metals will lose their electrons and non-metals will go cool. They'll pick them up. So usually somebody will pick up the electron. It's basically always what happens is if somebody loses an electron, somebody else will always pick up an electron. It's actually a type of reaction which is referred to as a redox reaction, which is when somebody loses an electron, somebody else simultaneously has to kind of pick up the electron along the way. And that's really how we get ions that are charges. And that's why when we look at something on the periodic table, for example, they don't have charges when they're by themselves. They only really pick up charges when those two guys kind of get together, a metal and a non-metal get together. Because as we'll talk about when we talk about periodic trends, they have opposite periodic trends. Metals really want to get rid of their electrons. Non-metals really want to kind of pick up electrons. So that's why when those two guys kind of get near each other, we get a transfer of electrons that actually happens. Yeah, in terms of electrons being transferred, there's always an equal sort of transfer, a balance of transfer of however many electrons somebody loses, those electrons will be picked up by somebody else. Yeah. Other questions? Okay. So in general, when we do have an ion by itself, like aluminum or anything that's positively charged, we're going to talk more formally about naming in the next chapter, but if you want to name just the ion, you basically just use the whole name of the element. So anything that is positively charged, that's an ion. If you see the formula for it, it should have the actual charge, like we see here, Al3 plus. If you were going to write the formula for this cation, because it's an ion, it should have the charge, and this would be known as the aluminum ion. If you had Na plus, it needs to have the charge written, and this would be known as the sodium ion. And even if you had H plus, that would be known as the hydrogen ion. So if you have anything that is a positively charged ion, you basically use the whole name of the element and you put ion at the end of it if you're going to name it. Any questions on that there? Now, anions are opposite, as we talked about. They are the ones that are losing electrons. And I'm sorry, they are the ones gaining electrons. So anions are the ones that are gaining those electrons, really from the ones that are losing electrons. And when they gain electrons, they become negatively charged. And we could also represent this in equation form. If we take something like chlorine and add an electron to it, we get something that has a negative electron here. Now, in reality, we know that chlorine actually comes as a diatomic molecule, which means really we have not one chlorine, but we have two chlorines, which means each chlorine needs to pick up 2 electrons, and that will give you 2 of these Cls with a -1 charge. Yeah, so that's really the balanced equation. But here, when we write one for gaining electrons, we see the electrons on the reactant side. And on the product side here, we see our ion that's being formed. Same thing if we did something like fluorine. Basically, fluorine would pick up 2 electrons, 1 for each of the fluorines that are present, and we would get 2F minus in this case. And again, we would see this on the reactant side, and this obviously on the product side. So just like before, we can basically write an equation to show an element gaining an electron, and that is how we could represent it there. Any questions on that? Now, when we have a negative ion, we actually drop the last part of the name and we put IDE at the end. So guys that are negatively charged, we drop the last part of the name and put IDE. So instead of chlorine, the Cl minus would be the chloride, IDE at the end. Instead of fluorine, this would be fluoride. If I had Br minus, this would be bromide. Yeah, IDE ion here. And again, just like the positive guy, if you were to write the formula for just the ion, we would show the charge in it. Any questions on that there? Now, when we put together a positive and negative guy, we always want to make sure that it equals 0 when it comes together. But before that, let's talk a little bit about the periodic table and charges. Now, on the periodic table, there are certain things that have fixed charges. So everybody in group 1 will be +1. Everybody in group 2 will be +2. Really, group 3 is that guy right there, which will be +3, which is aluminum. The staircase kind of crawls down this way. So skipping group 4, going the back ways, and this is really the non-metals. This is going to be -3, -2, and -1. So the non-metals in this case are the ones we're talking about here, because underneath the staircase, those are actually metals. Yeah, so above the staircase where the non-metals are going to be the -3, -2, -1. So you go +1, +2, +3, skip, and then go -3, -2, -1. So go up to 3 and down to 3. There's no real good group there or formula there for group number 4, as there's a lot going on, metals, metalloids, and stuff in that particular group. That means that sodium will always be +1 no matter what the deal is, no matter who it hooks up with. You'll never find a sodium with like a +2, a +3. It will just never happen. And the reason really it will never happen is kind of what we were just talking about a second ago. Energy-wise, after it loses that first electron, you have only those core electrons, which are super close to the nucleus. So good luck trying to rip it off. It just doesn't happen. So just that one outer electron is the one that's able to lose, and that's why it becomes a positive one charge. Now, this is our transition metal, which could have a varied charge, but there are 3 exceptions in the transition metal that will always have a fixed positive charge. So that is like our zinc, which is right around here, and our cadmium. These guys will always be +2. And if you hang a left there at cadmium, you'll find silver. It will always be +1. So those 3 right here, although they are transition metals, and although most transition metals have a varied charge, and what I mean by that is something like copper could be +1 or +2 depending on the situation. Something like iron can make a +2 or +3 depending on the situation. But these 3 here that are transition metals, zinc, cadmium, and silver, will always have a fixed positive charge. Just like that, kind of where I circled over here, where there's kind of lead and tin on the periodic table, although they are not transition metals, they also are below the staircase and are metals, and they also can have a varied charge. So things like lead could be like +4 or +2, same thing with tin. So again, even though they're technically not transition metals, they are named the same way, as we'll talk about when we talk about naming. They basically are named the exact same way as we name transition metals. Any questions on that? So that's really important, those charges, as we go into naming, to understand, where those things make charges. Hydrogen, by the way, which is right here. Hydrogen is the unusual element that can actually go both ways. It can actually be positive in certain cases, and in other cases, it can be negatively charged. And if it is positively charged, as we talked about, it is the hydrogen ion. And if it is negatively charged, it is the hydride, IDE ion. Basically, if hydrogen comes after a metal, or it's attached to a metal, it will be the negative version. In all other cases, it's the positive version, basically, of hydrogen. Any questions on that there? Okay, so as I was mentioning, when we do put ions, or where we really do find ions is really in solutions. So having ions in solutions is what actually makes some solutions conduct electricity really well, and solutions that can conduct electricity are what are known as electrolytes. And electrolytes can conduct electricity because of the presence of ions. And when you have a strong electrolyte, it 100% breaks apart in solution. So something like sodium chloride, that's a sodium chloride solution. In sodium chloride, you no longer have the sodium and the chlorine together when it's in solution. The only thing you have is 100% sodium ions and chloride ions floating around in that solution. None of the whole units are still there. And what that does is, because there are so many ions in there, it's able to actually complete the circuit and conduct electricity really well. So we'll see a picture. If you put like an electrode that has a light bulb on it into a strong electrolyte solution, the light bulb will shine really bright because it's able to conduct electricity really well. The light bulb will turn on, it'll be really bright. There's also weak electrolytes which mainly stay together, but do produce a few ions. And in that solution, for example, here, we'll use something like HF, which is hydrofluoric acid. So hydrofluoric acid, when it's in solution, will mainly still stay together. So that is mainly what you have when you have like a hydrofluoric acid solution. It was pretty much the H and the F still together, but it will be able to break apart a little bit, and you'll produce a little of these ions. And that means that when you look at that solution, you have HF floating around, but you got a little bit of H plus and F minus. So because you still have a little bit of those free ions basically floating around in the solution, It's still able to conduct electricity, but nowhere near as well as a strong electrolyte. So for example, if you take the light bulb example with the electrode and you put it into a weak electrolyte solution, the light bulb will turn on, but it'll be like super dim. Yeah, so it'll be very, very dim, like it's losing power. There's not much going through there, but it's still able to be powered and stuff like that. Third type of thing is an electrolyte. A non-electrolyte, a non-electrolyte. And a non-electrolyte will dissolve, but stay together. And pretty much you get no ions. So for example, sugar is an example. Sugar is carbon, hydrogen, and oxygen. That thing is a thing that will dissolve, but it will not produce any ions. So because it does not produce any ions that have charges in that solution, it does not conduct electricity. So again, if you kind of throw your light bulb example into that, the electrodes, when you put it in there, the light bulb won't go on. Basically, it'll stay off because it won't be able to conduct electricity. So what makes something an electrolyte is the presence of ions, and the more ions you have, the stronger electrolyte it is. The less ions you have, the weaker electrolyte it is, and no ions is a non-electrolyte. Is pure water something that is a good conductor of electricity? Pure water is a lousy conductor of electricity because pure water is just water, which is a molecular compound. There's no ions. Now, just so nobody goes home and electrocutes themselves, the water that comes out of your faucet, like when you're taking a shower, is not pure water. They actually throw ions in there to clean it. Yeah, so you will electrocute yourself if you want to, blow dry your hair in the shower. Yes, because it will conduct electricity really, really well. But if you have just pure water that has no ions in it, it should be a very bad conductor of electricity because there's really no ions to complete the circuit. So once again, do not blow dry your hair in the shower because you will get electrocuted. Oops. That's the example is what I was talking about there on the left. Pure water, bad conductor of electricity because again, there's no ions floating around there. Any type of salt, which is an ionic compound, will break apart 100% into ions. So this solution has a lot of positive cations and anions floating around, and it helps conduct electricity. And again, that light bulb will go off pretty brightly. Any questions on that? Yeah. Yeah, I mean, there is those type of things are the same things like when you get and drink Gatorade or Powerade or whatever those type of things are those electrolytes in your body. Your body needs all those sort of nutrients, like those ions and stuff, to help keep everything flowing well. So an ionic compound, when they do come together, looks something like this, and they do in the solid form try to maximize the attractive forces and minimize the repulsive forces. By the way, the Cl minus, which is the negatively charged one, looks bigger than the positively charged ion because when somebody gains electrons, the size of the negatively charged ion is larger, just like we talked about with the guy that's positive. When we make an anion, the electrons are added to the electron cloud, so the negatively charged guy starts to kind of grow its electrons, and the overall size of the negative ion is larger than the neutral ion in that case. That's why we see it like that. So this is really what salt looks like before you dissolve it. When you dissolve it, you're able to dissolve it because we take something like water, which actually has a negative side and a positive side. Hydrogens are more positive, oxygen is more negative. So when you throw a bunch of water on here and you start mixing it, what happens is there's so much water, it's able to actually pull off those ions. And the positive ion will be surrounded by the negative side of water, which is the oxygen. And the negative ion would be surrounded by the positive side of water, which is the hydrogens in this case. Right, and we help this along by stirring, right? We add energy, we also splash water all over the place. And before you know it, that salt will dissolve and we can't see it, right? And it's still there because when we would heat, say, our salt solution, like we did in an earlier experiment, what happens is we evaporate off all the water, right, that's around each of those ions. So now those ions are free to pop back together, and we see the solid come back, right? And that's sort of what we did with the evaporating dish on those earlier experiments where you heated it up and there was no solid really in there, right? And then after you heat it up, you have some type of residue in your evaporating dish, and that was your salt coming back together because you basically got rid of all the water that was in the way, that was keeping them apart. So that's really how something dissolves. A salt, an ionic compound, dissolves by, you throw water on it. There's so many water molecules. You add some energy by mixing it around. They're able to really pull off each of the ions, and they are able to keep those ions away from each other because there's a very strong attraction between the positively charged ion and the negatively charged ion that they would want to come back together, but there's so much water in the way, it keeps them apart. And that's why it really doesn't go anywhere. It really is no chemical reaction happening. We just visually can't see it because there's just so much water in the way, right? So it kind of disappears from our ability to actually see it when it has all the water around there. We're unable to really re-see it when we get rid of all that water, and those guys are able to kind of come back together to make the solid. Any questions on that? All right, so when things do get charges, as I talked about, it really does only happen when metals and non-metals really get together. That's really when things have charges. And when it happens, it's always a transfer from the metal to the non-metal that gains the charge. But when we write a formula for an ionic compound, and an ionic compound is always a metal and a non-metal together, and it always is a transfer of electrons from the metal to the non-metal, and that's going to result in our cation being formed, which is positively charged, and our anion being formed, which is negatively charged. Now, whenever we write that formula for an ionic compound, the overall charge has to equal 0. So that means when you put the positive ion together with the negative ion, you need to do it in a way that gives you an overall charge of 0. And you need to do it in the simplest way that will get you to 0. There's many ways to get to 0, but you want to do it in the simplest way for it to get to 0. So for example, if we take sodium, which is group 1, +1, and we take chlorine, which is group 7, is -1. When we put them together, +1, -1 gives me no charge. So when we write a formula that has both a cation and anion, a metal and a non-metal together, it is always the positive guy first, followed by the negative guy when you write the formula. So the sodium is positive, negative guy is chlorine. So those are always the two ones that come together. Always positive, then negative. And that goes both with the formula and also when we talk about naming, it's always the positive guy first and negative guy when you go to name it. The actual formula itself has no charge, but it is actually made up of two things that do have charges. In this case, it's made up of a sodium that has a +1 charge and a chloride that has a -1 charge. And if we put our name together in this case, whole name of our positive guy is sodium. The negative guy gets the IDE at the end of it. So that is how we get to our sodium chloride name in this case. We took a calcium, which is group number 2, and we took a chloride, which is group number 7. When we put this together, if we put it together just like it is, we would end up with a +1 charge, which is not good. We actually need not 1 Cl-, but we need 2 of them. That gives me a -2 overall to balance out the +2 that we need. And then at this point, you just write what you did. We have 1 calcium, and I have 1 and 2 of these guys. And that would give us our proper formula in this case. And if we were to name this guy, we would use the whole name of the metal, which is calcium. And the chlorine would get the IDE at the end of it. And this would be calcium chloride. By the way, is there a prefix on that name that I just wrote? There is no prefix. People want to go like calcium dichloride because it seems more chemistry-like, but it's not. It's just wrong. So in this type of naming, as we'll talk about, there really is, doesn't matter how many of either one of those guys that you have, you never use any type of prefix. So it's just the whole name, IDE for the second one. If you have 40 chlorines at the end there, it will still just be chloride at the end. Any questions on that? There's also other things to the naming part that we'll talk about. So if we look at some other examples here, barium +2, group 2, oxygen group 6, -2. We just need 1 of each. So just BaO. Here, aluminum, which is group 3, has a +3. Sulfur, which is group 6, has a -2. So the common number there is 6. Yeah. So again, to get my aluminum and my sulfide, to get this guy to 6, I need 2 of these. Gives me a +6. And to get this guy to 6, I need 3 of those. Gives me a -6. And that is how I get to my formula. I have 2 aluminums and I have 3 sulfurs. And that gives me the proper formula. Now, sometimes people are taught to do this move. You know, just kind of bring the number up and down and cross over. And you could do that, and you could do it blindly. If you're good with like 93% of the time it works, it does not work 100% of the time. So it's best to think about when we put these things together, try to get to a 0 charge. If you just blindly kind of flop the numbers. So what I mean by that is sometimes people are taught, oh, all you got to do is just, you know, take that down there and that down there, and you get Al2S3, which again does work a lot of times, but there's a lot of places where it doesn't work, just blindly kind of swap in the numbers. So I wouldn't personally recommend it. I would think about it as balancing out the charge to 0 so that you hopefully will get the right formula. There's actually a reason why we have to balance this out to 0 in the simplest way, and it has to do with the bonding aspect that we'll talk about. But basically the idea is the noble gases. This is the simplest way for each of these guys basically to get to the noble gas electron configuration. It'd be just like the noble gases, which is that stable configuration that they're looking to do. And that's why we always want to make sure it equals 0. Lastly, there we have potassium and phosphide. That's group 5, so it has a -3 charge. Group 1. So in this case, we need 3 total of the potassiums and 1 of the phosphide in that case. The name of the first guy would be barium oxide. The name of the second guy would be aluminum sulfide. And the name of the last guy would be potassium phosphide. And their bird, was it? No, they hit the window. No. All right. Any questions on that? All right. That is chapter 4.